Okay.
Yeah, sure.
Okay. Okay. Hello, everyone. Welcome to attend our EIC workshop. I'm Keni from Capital Normal University, and the other co-chair in this workshop is Dr. Lei Yang from George Mason University. Okay, it's our great honor to have you in the first international workshop on edge intelligent computing at ESWeek 2022. In this workshop, there are 7 talks in total. We'll have 1 keynote, 2 invited talks, and 4 regular presentations. The 4 regular talks are selected from 12 submissions, and 1 of them will be granted a Best Presentation Award. The 3 judges from the Best Presentation Award are Dr. Ying Wang with the Institute of Computing Technology of Chinese Academy of Sciences, Dr. Weiwen Zhang with George Mason University, and Dr. Xianzhang Chen with Chongqing University. So first, we are delighted to invite Dr. Ying Wang to give the keynote. Dr. Ying Wang works with the Institute of Computing Technology of Chinese Academy of Sciences. He was named as president of the IEEE ACM Design Automation Conference on the 40 Innovators Award. His research interests include reliable computer architecture and VLSI design with an emphasis on memory systems, energy efficient accelerators, and approximate error tolerant computing. Okay, so today, Dr. Wang will give a talk on the topic of towards agile development of specialized processors. Okay, let's welcome Dr. Wang. Because of internet connection issues, the internet connection issues. So Dr. Wang prepared a video for the keynote.
Yeah, thank you so much, Professor Wang. Yeah, in order to guarantee the quality of the presentation, he has recorded the presentation in advance. So after the presentation, please feel free to ask questions. And I saw that Professor Wang is already in the Zoom, so prepare your questions and you can ask after the video. So we can start the presentation now. Thank you, Professor Wang, again for your coming.
Good morning, respected audience and chairs. This is Wang.
So can you hear the see the video and also hear the voice here?
Yes.
Okay.
Yep.
Thank
you. From Institute of Computing Technology, Chinese Academy of Sciences. Thank you very much for letting me speak in the first talk of this workshop. Today, I'm going to share some of my recent work on how to quickly customize a specialized processor, especially the neural network chips for specific tasks. Let's begin with the background of this talk, why we need processor specialization in current AIoT era. In the past years, we witnessed the fast growth of smart devices in the electronics market. It has beaten the share of traditional PCs and mobile phones. It's not unexpected because edge devices have high diversity and great volume when it's compared to the centralized fog and cloud machines. IoT devices favor specialized architecture, particularly specialized processor chips, due to many reasons. The first is the application-specific architectures have higher energy efficiency when compared to general-purpose processors or configurable devices. The other reason is specialized architecture could have lower cost and a smaller chip footprint, which is also very important for IoT applications. Specialized processor like the neural network units, aka NPU, has made great success in this day's market by beating general purpose processors according to some statistic sources. Unlike the cloud-oriented NPU like the NVIDIA or Capricorn products, which put more emphasis on high computing power and high programmability, the edge or terminal NPUs are focused more on energy efficiency. Sometimes they are required to deliver high performance only for one or several tasks, and they can afford to sacrifice some extent of generality or programmability to trade off for low power operation. Such examples could be found in the market of IoT devices. This specialized NPU used for image processing, aka AI ISP, they only need to support one or several image enhancement network models, or the security camera, which only need to take care of a human or object recognition task. These chips can trade off unnecessary generality for energy saving or product cost down. Actually, it's very important for AIoT chips to reduce its cost, especially the non-recurrent development cost, aka NRE cost, because the AIoT hardware market is highly diversified and segmented. You cannot amortize the huge NRE cost amongst the small volume niche market, except for the cost. The time to market is also very important. Take one of the chip I have been responsible in 2018 as an example. It's the ICT 5PU chip. We designed two specialized core in its SoC. One is NPU core. The second is the video streaming and processing core. This SoC takes more than 15% months to tape out, and it lasts 19 months from the project kickoff to running Hello World example on this chip. This is actually very expensive in both time and cost for IoT devices. So how to reduce the processor development cost and the time to market? I think we should take a look at the design flow of a specialized processor chip. Roughly speaking, it takes multiple major steps, each of which take quite a lot of human effort. The first step is the architecture design phase. And then you have to build a high-level model, conduct design space exploration with this model, and then do RTL coding, aka front-end design. Then go verification, physical design, finally to fabricate, testing, and packaging. Next, we will introduce some of our work related to each step of the whole design flow and see what we can do to reduce a little bit of the development cost for specialized processor design. In this flow, the first and foremost is to change to the front-end design phase. Let's take the neural network chip design to exemplify our research on specialized processor design automation methods. For example, early in 2016, we released the deep learning framework. It could generate the neural network accelerator and RTL design when given the network description from Caffe or TensorFlow model. So people don't bother to write code for accelerator implementation. Just take one click to generate the accelerator design to realize this neural network model functionality. After that, we also upgrade the deep learning framework to support graph neural network accelerator customization. In 2018, in deep learning GL, it received description from software framework like DGL or PyG, which is widely used framework for graph neural networks design. So the deep learning GL will automatically generate the RTL design for the targeted neural network accelerator. This accelerator is customized for that single GNN model particularly. Today, when we still work on the optimization of the deep learning framework, there's some issue unsolved by previous deep learning work. We found that either when we generate or handcrafted NPU accelerator design, we actually faces mostly two choices of architecture. because current AI accelerator architecture can be roughly divided into two categories. The first is generic architecture, which processes neural network model layer by layer without pipelining. This generic NPU architecture reused the single processing element array, which is PU, across all the layers of neural network models. Suppose we have a 4-layer model. This generic NPU will process a single layer at one time. After finishing one layer, it writes back the produced features back to the memory and then load the next layer. It repeats on and on in this way to the final layer. Typical generic architectures are like Dianao, Iris, and TPU. Our work on DeepNGL and Engine also belong to generic architectures. And it goes to another level by mapping the graph processing operators to the NPU array. So it can even unify the graph aggregation and feature extraction stages belonging to one GNN model. The shortcoming of the processor is obvious. The first is that the same processor array unit cannot adapt to different layers which have different characteristics in terms of the layer dimension or the CTC ratio. The CTC ratio is the computation to communication metric for one neural network operator. The CTC ratio determines the peak performance of this operator can reach by running on a specific hardware. So when operators with different CTC ratio and layer dimension are mapped onto the single processor element array, it leads to low resources utilization. Besides, after finishing one layer, the processing unit will write back the results to memory. So there's a high cost of data exchange to memory between layers. This is because the generic architecture, and there's a lack of pipelining mechanism that moves results directly from the producer PE to the consumer PE, making the memory bandwidth bottleneck worse. The second choice is the full pipeline architecture, which processes 4 layers in a pipeline manner. For example, given the same 4-layer network model, it will have a 4 hardware pipeline. Each pipeline has one processing array. The advantage is that it has a customized processing array with the resources configuration perfectly matching every single layer. And also, the intermediate results generated by one layer do not need to go to the memory. It could directly be forwarded to the next layers that consumes them, either by interconnect or the register caching. So it results in better memory bandwidth utilization. However, there are also issues in this implementation choice. The most important is the scalability issue. Sometimes it is even impossible to assign the limited resources for the very deep neural network models because it's constrained by resources budget. Suppose we have 130-layer ResNet model. Such a full pipeline will be very, very expensive due to the pipelining overhead. In addition, such a customized hardware for pipeline can hardly be reused across different models. We totally lose programmability, not scalable to different workloads. Do we have a third choice? Can we preserve the good of a full pipeline architecture and still keep the scalability of the generic architecture with customizing a specialized NPU? To address this problem, we aim to propose a novel class of design solution for DNN acceleration, which is the segmented array pipeline architecture for NPU specialization. In segment pipeline architecture, a SPAR for short, we can partition the NN model into similar segments and process the entire model segments by segment. By pipelining the layers within a segment, memory accesses to intermediate results can also be eliminated. So we have better memory bandwidth utilization like the full pipeline architecture. At the same time, the scalability and generality issue caused by full pipeline can also be relieved to some extent because each segment contains only a small number of layers. This segment can also temporarily share and reuse the same processing array pipeline. So we avoid over deep pipelining. and keep the efficiency and the programmability at the same time. Here, we did a simple experiment to show how the proposed SPAR architecture beat the generic architecture in the metric of a CTC ratio. If a network running on the hardware show a higher CTC ratio, it means it induces less access to the memory. According to the roofline model, operators with less memory accesses have higher chance of reaching the peak performance of the hardware. As we can see from the figure, the average CTC ratio of a SPAR is pretty close to that of the full pipeline architecture, but it has a very shallow pipeline and containing only several stages, not like the full pipeline architecture has the same number of pipelines as that of the layer number of the network. Now we have the basic concept for SPAR architecture. It also has a large design space to explore when used to customize a specialized NPU architecture. The customized and efficient pipeline architecture for a particular workload must address three features. First, the SPAR design should be flexible to run different segments. Because a deep network can be partitioned into many segments, we must guarantee these different segments can be mapped to the SPAR pipeline with high utility. Second, there are many ways to divide the network, especially when the network is very deep. Multi-partition models plays an important role in the accelerator performance. We must carefully partition the AM model and assign the layers in a segment to proper pipeline to make sure each operator have a high resource utilization. Third, we need to jointly optimize the resources allocation for all the pipeline, including memory,
You're muted, Professor Yang.
work in the pipeline. And no matter how many PUs or how many processing elements in the PU, or how big is the PU buffer, to make sure a neural network segment can run in this PU in pipeline. The second feature is data flow hybrid pipeline design. This is because a random layer in a segment have different preference for data flow, like wait stationary, output stationary. We must be able to configure the data flow of PUs after segment switch to make sure all layers are operated and with the best data flow. We add multiplexes to the PEs and enable the PE array to choose between wait stationary or output stationary data flow. In addition, SPAR allow data flow mix and switch without having to transform the data layout of the generated intermediate feature maps. The third feature is the data dependency between the pipeline will vary to different segments. For example, running segment 1, PU1 send results to PU2, but for segment 2, PU1 receive results from PU2. So the inter-PU fabric needs to be configurable. In the SPAR design, we adopt a non-blocking network, beneath network, which allows unicast and multicast transmission without data conflict between the PUs. Besides, we reduce the connection overhead by trimming the unnecessary freedom of interconnection. When we have the basic SPAR template, we can customize the specialized SPAR design for one or multiple neural network models. So the next step is the co-design phase that decides the software and hardware parameter used to implement the final solution. This design space exploration loop includes two modules. The first one is the model segmentation unit that partitions the targeted models into segments of layers. And the second module is to decide the resources allocation for the pipeline that operate these segments. Unlike previous hardware and software co-design exploration methods, which mostly adopted two loops optimization, our co-design is two-step optimization. No iterative search is required, and this search process sends two modules decoupled. And the results of the model segmentation can be used to generate SPAR designs under different hardware constraints. Particularly in the first step, we formulated the model segmentation problem as a mixed integer programming problem with two objectives. First, we aim to maximize the CTC ratio of all segments in the partition process so that a dedicated accelerator can be designed to better meet the bandwidth requirements of these operators. Second, we make sure the segments have similar shapes so that when we map the segments to the same pipeline, the spot pipeline will have better load balance, making sure all of the pipeline PUs have high utility. In the second step, we propose a heuristic algorithm to allocate hardware resources for each PU pipeline. We normalize the load distribution and bandwidth requirement for all segments from the first step. Then we allocate the resources based on the normalized results of the segment gaps to achieve load balancing and better bandwidth utilization. This step will determine the resources allocation for all segments at the same time. This step makes sure that all the segments will have similar CTC ratio in this pipeline. Secondly, we also readjust the resources allocation for the specific segment if this segment plays a more important role in overall performance than the other segments. Finally, these three steps form the proposed deep learning SAC design generation flow. We can specify the design goal and the resources constraints as input together with a given DNN model description. Accordingly, the SPAR framework will generate the accelerator co-design solution, including the hardware parameters and the model segmentation results. Once the co-design solution of the targeted DNN model is determined, a customized pipeline accelerator can be derived from the hardware template, and it will execute the segments sequentially. In evaluation, we implement the SPAR accelerators with the same hardware resources budget as that of Iris, HTPU, and NVDOA. When customized towards a particular network model, SPAR accelerators achieve an average 3 times speed up over these ASIC-based accelerators, thanks to the increase of resources utility and the increase of CTC ratio. We also compare the throughput and the DSP efficiency with the state-of-the-art FPGA-based neural network accelerators, either auto-generated or handcrafted. Our design outperformed the other pipeline design in FPGA because our shallow pipeline SPAR design can be reused flexibly by the network segments and also have fewer operation bubbles in the pipeline, lower pipelining overhead. For the same benchmark and the same FPGA devices, both the resources utility and the performance measured in GOPS are much higher than state-of-the-art work on FPGA acceleration. In deep learning SAC, except for the architecture design, we can also see that the design space exploration and architecture modeling are also very important to the final performance of a specialized processor. However, in the deep learning frameworks, the architecture modeling and the parameter exploration methods is ad hoc for the SPAR architecture for the generic neural network processor. What if the architecture is an arbitrary type of a processor, say ISP or VPU or even CPU? In the field of architecture design, at the early design time, we need proper resources reallocation, such as memory computing resources bandwidth, to achieve better performance and energy cost trade-off when it's specialized for one type of workload. But due to the tremendous configuration space and the complex interaction between these configuration parameters, how to determine the optimal hardware configuration and the appropriate amount of resources required by the target task remains a significant challenge. Especially for most of the time, the design exploration methods is not transferable from processor to processors. One DSE framework cannot work for another if we change the processor architecture, say from the MPU to CPU to ISP. Currently, to deal with the parameter exploration or resource allocation problem, machine learning is helpful. These ML-based approaches first train a model to predict the system's behavior, which acts as the performance predictor. Then we train a resource scheduler to do the resources reallocation to select the design parameters. However, these ML-based approaches still have several shortcomings. First, the high runtime overhead, as they have to tentatively evaluate a group of possible configurations and then decide the best one. How to build a model to evaluate different types of processor is not easy. Second, to suffer this data scarcity problem, they need lots of training samples to improve the prediction accuracy. Every time you switch to another processor architecture, new data are required. This problem above made us think, can we have an explorer to generate the Pareto optimal configurations directly? And can we use the exploration framework across different processor architecture, but do not need to build the prediction and allocation models? The idea is quite straightforward. It is inspired by the generative adversary learning, aka GAN. At first, we built a performance-based model based on neural networks and then connect it to the configuration generator. And they work to optimize each other until the evaluator generates accurate evaluation of the performance, and the configuration generator generates the best configuration that meets the performance constraint. More precisely, here is the architecture of a quaternary GAN, which holds 2 generators and 2 discriminators. And so all generators and discriminators get improved in the minimax game. And the game ends until the 4 players are at a Nash equilibrium. When we use the proposed DSE method for processor customization, it generates the most energy efficient processor design solution when compared to the baselines. It incurs only 3% more energy cost than the Oracle. We have seen how we reduce the cost of the design flow of front-end design and DSE. Now, let's see if it's possible to skip the most expensive step of chip design, which is the physical design and fabricate stage. Actually, chiplet reuse may be a possible way out to customize a specialized processor without physical redesign. And chiplet reuse do not need to tape out a new chip. It reuses the available chiplets to build a new system. However, it is still not as agile developing a PCB board system, because even when we reuse the off-the-shelf chiplets, we have to manufacture the silicon interposer, which is like a new chip itself. If we can eliminate the interposer design and manufacture stage, it will become more agile. Thus, we propose a general reusable interposer design to fast build chiplet-based processors. This interposer, named GEAR, has a reconfigurable interconnects for both active and passive silicon solutions. With this reusable interposer, the chiplet system can be built just like the Go baseplate. And we also have chiplet system design automation based on this reusable interposer. GEAR is a general interposer and design flow for agile specialized chiplet system design. When we return to the neural network processor, can we have a better design of the interposer, particularly the network on interposer, so that we can reuse a single type of NPU chiplet to build different NPU products for segmented markets from edge to cloud. Such an interposer can be reused and reconfigure itself its interconnection to integrate different number of chiplets and practice different parallel computing models according to the product profile. However, due to the limit of time, we do not go to the details. Let's have a wrap up. We introduced some of our recent work for the architecture design, hardware generation, and the design space exploration, especially for AI accelerators. We show that the SPAR architecture strike a balance between the general and the pipeline architecture. And the deep learning SAG flow based on SPAR architecture is suitable for the specialized NPU design by generating pipeline architecture. To help processor design exploration, adversary machine learning can be used to reduce the modeling cost. when we switch to different processor architecture design. At the end of the talk, and thank my colleagues and the students who did this work. Also, thank you very much for your attention. Thank you.
Thank you so much, Professor Wang. Yeah, it is a great talk about the front architecture, actually including hierarchies from the architecture design to the software design. Yeah, personally, I'm extremely attracted by the hardware and the software co-design there, since it is huge design space to explore. And Professor presented the whole framework to us. So thank you so much again. Yeah, it's time for our attendees to give your questions for Professor Wang. If you have, you can feel free to unmute yourself and raise your questions here.
Yes, Professor Yang, can you hear me?
Yeah, we can.
Okay. So any questions?
Thank you. So if you have any questions, just unmute yourself and raise your questions. So,
Yeah.
Go ahead.
So thank you, Dr. Wang, so much for the great talk. And a question about the proposed segmented architecture in the SPA. So my question is, when an SPA architecture is customized for a particular or for specialized work, can it support some other neural network models as well? If yes, then how about the performance?
Oh, okay. That's a very good question. Thank you, Keni. Actually, I have conducted an experiment to test the efficiency when we generate a specialized SPAR accelerator for one specific neural network model. For example, we have we have generated an accelerator for ResNet, and this accelerator is customized for ResNet network model only, but it can also run the other type of a model like a MobileNet or SqueezeNet. And we also compare the performance of SqueezeNet and MobileNet on this AlexNet dedicated accelerator. And we see that the performance of the SPAR architecture is still higher than the generic architecture because it has higher CTC, it reach higher CTC ratio on its hardware, and the memory access overhead is much lower than the generic architecture. So the results prove that even when we generated a customized accelerator for a particular network, it can still and deliver decent performance for other networks. And so that, I think this is a very good characteristic for the edge smart devices. We lose some extent of generality, but still have a very good programmability to support different kind of models, even when we do the customization. And if you're interested in the detail, you can see our paper on the Micro 2020 proceeding. Yes, I think I hope my answer addressed your questions. Thank you.
Okay, that's a great result. Thank you.
Thank you, Dr.
Thank you.
Yeah, any questions from the audience? Yeah, if you are thinking some questions, I can raise one quick question here. Dr. Wang, thank you so much. Actually, I have one quick question about the, I'm interested in the neural network the processor design about the accelerator generation. So can I know whether you have the specific requirements from the applications, or you are focused on the general applications, or there will be one domain of the applications you are focused on?
Oh, okay. Thank you, Professor Yang, for your question. if I understand your question correctly, I think yes, we have some constraint for the application. For example, for the deep learning stack, we see that the experiments is all about the neural networks, but actually it's not have to be neural networks. If your application can be represented by a static task graph, and it can be described in the it can be described in our given format. If it's not given by the Caffe or TensorFlow, we can still generate an accelerator, a pipeline accelerator for your specific algorithm, no matter it's neural networks or not. Actually, we are working on the next edition of the deep learning, which is supposed to operate for the dynamic task graphs. So if we can support both static and dynamic task graph, I think many different applications can use this mechanism to generate accelerators. Yes. Okay. I think the problem is that for neural networks we have the frameworks like TensorFlow or Caffe. People get used to it, but for other types of applications like image processing or video processing, actually we don't have such popular frameworks and that can give the exchange files to our deep learning tools. So I think that's the one of the difficulty prevent our framework being used to other types of workloads. Yes.
Thank you so much for the answer. Yeah, sounds great to know that it is the framework that is powerful for domains of the applications if we can represent the applications in some format, right? So thank you so much for answering the question. So any question from the audience? If not, we can move to another. Yeah, I think Dr. Wang will stay in the Zoom. So if you have any questions later, you can type in the chat box. And thank you so much, Professor. If you see the question, you can answer that. Thank you, everyone. Thank you. Okay, so yeah. Keni, you will do that or I will continue?
Yeah, yes.
Okay, so thank you again, Dr. Wang, for your great presentation. And also it is our great honor to have you today. So we are happy to present this certificate to Dr. Ying Wang for the academic keynote in our first international workshop on the edge intelligent computing, the EIC, co-allocated with ESWeek 2022. So personally, right, I'm extremely attracted by the presentation about towards the development of the specialized processors. So in regard of the workshop by Keni and me, Lei Yang, it's our great honor to give the certificate for the presentation by Dr. Ying Wang. Thank you so much again. Thank you.
Thank you, Lei and Keni. It's my honor.
Thank you.
Thank you.
So we will oh no, this is not there. Can you see my screen now? There.
Yes.
Okay, we will move on our next invited talk. This invited talk is will be by Shuaiwen from Sydney University. So he will talk about the exploration about the design space of the future planning scale of AR system. So to give a brief introduction about Dr. Song. Dr. Song is the director of the Future System Architecture that is FSA lab. So he's the SOAR faculty fellow, associate professor in the School of Computer Science, the University of Sydney. So his research interests include the computer system architecture, high performance computing. Also, these are with the particular interest of the holistic system design and software hardware co-design. So it's our great honor to have Professor Dr. Song here today to give his talk. So feel free to share your screen if you are ready to start. Dr. Song, thank you.
Hi, thank you, Lei.
Thank you. I will stop sharing. Thank you.
Trying to print this.
Yeah, it's coming.
You guys see my screen?
Yeah, perfect.
All right. Thank you, everyone. I'm Liang. I direct Future System Master Lab at University of Sydney. I'm also a joint professor at UW Seattle EE department. Today, I'm going to just briefly talk about our recent work on the design roadmap for future planet scale extended reality systems. And this thread of work in my lab, we do different types of software hardware co-design for emerging applications, and extended reality is one of them. We also do work in machine learning system a lot. And occasionally we do design accelerators like the previous speakers were focusing on. So this talk is focusing on our recent 3 works in the topic of planet scale XR system design. And this is a collaboration with University of Washington. I want to first acknowledge my students as well as my collaborator, Michael Taylor from Bespoke Silicon Group, and his PhD student, Wang has helped a lot in terms of some of the hardware design part. And these, I'm trying to give this talk just to trigger interest in this new area of software hardware co-design for these emerging types of applications, including virtual reality, augmented reality, and etc. So here I'm quickly going through the 3 recent works and show the high-level interesting observations, and hopefully this can start some conversations, and we'll have more people working in this research directions, and to exchange some thoughts and discussion. So I won't really go into too much of the technical details. I want to give you a bigger picture of what we see and what are the potential directions for this thread of research. You probably know XR, extended reality, is a niche research area, but although it's niche, it has a big market and impact. So every 10 to 15 years, we see an impact shift in the way people use and interact with technology and data. And now we're after PC, internet, mobile, we're in the era of extended reality, VR, AR, MR. The market value in 2020 has become a $30 billion business. The research values is also very interesting. For this thread of research, as a computer system architect, it's quite fascinating because it's multifaceted, encompassing research areas that from not only computer graphics but also perception research, HCI, and system architecture research. So all the things we really care about in this field: performance, real-time constraints, power, energy efficiency, user perception, quality of experience, approximate computing, machine learning, deep learning type of co-design, multi-accelerator, system on chip, parallelism, consistency, et cetera, it's very unique in a way that you have to look at this as a multi-accelerator system, and you have to consider a lot of factors when you design things for these type of applications. Now, today's talk will be focusing on some interesting challenges and key insights and takeaways, some high-level design concepts, and some future works. So we have, recently we have some more work coming out, but in the past we have 3 signature works. we did the VR, one of the first VR papers at HPCA 19. This is identifying the commercial VR systems, more tethered desktop-based systems, and then it's issues with kind of real-time user experience problems and connect that to computer architecture and system and operating system. And then we did the ISCA paper for how you design future chiplet servers for parallel rendering. And last but not least, a recent paper last year about how do you do highly efficient, high quality mobile and cloud VR collaboration. So there's no need for this introduction. You have experience, we're in this kind of virtual reality immersive experience is very important for different fields of studies. But based on the, what we have seen in terms of the gaming industry, the resolution, the real-time constraints, all these immersive effects, lighting effects, etc., has demanded very high performance from our hardware. But really, if you project from current Moore's law trajectory, we'll see about 50x kind of performance gap to actually achieve immersive environment. And then the first challenge we want to talk about is we really need to how do we really need to get this concept of immersion? These type of hardwares are tethered, things like Oculus Rift Tower. These are desktop, very powerful GPUs supporting connected table to your VR glasses. Let's take a look at what's actually on the market for like Oculus Rift for high quality VR scenes. And this is a test for Sponza VR. In this scene, you will see when we move around, you can see there's some kind of motion, judder, also a little bit kind of latency and disorientation. And you will see this on the screen, there's a flashing C appearing. So we'll use that later, just keep in mind. So really, the two factors that determining the real-time user experience with VR, one of them you're quite familiar is rendering, frame latency, and that's for sure. The other one is what makes VR devices more signature, more user interactive, is something called motion to photon delay. It's basically, you can understand this as when you move your head, how long will take the actual image to be projected on your display near your eyes. So when user movement, so in other words, when user movement will be fully reflected on the display screen. So if it's too large, then you will become really blurry and have a lot of motion sickness. When you reduce it to 50 milliseconds, it's much better. 20 milliseconds, you can tell there's still a lot of in sync, sort of not in sync, but you still can tell much better in terms of presentation. So industry standard recently is around 20 milliseconds when they design these VR scenarios, but really 7 milliseconds is an ideal threshold. So for users to feel they're actually in the immersion and they don't have a lot of motion anomalies, right? So the research challenges here is how do we leap closer to true immersive experience? Now we used off-the-shelf Oculus Rift Tower to profile this number with the MPD, and you can easily tell for these games that a lot of them in terms of MPD is way over 7 milliseconds. Some of them even over 20 milliseconds. And a lot of time, that's exactly why you see the motion issues that we have observed earlier. For more data, you can look at our paper. So we really here becomes we did a lot of studies and evaluation of paper, and eventually we find this is an opportunity to use processing in memory. Specifically, back then we did this research with hybrid memory cube as the PIM device to enable these combat VR motion anomalies. So quickly go through this. We understand the user very strict real-time constraints. So the rendering for each frame may take several display refresh intervals. So which causes long MPD, so makes the project, when you move your head with your headgear, the object is displayed in a wrong head-mounted display position. So people will feel things like very kind of vision blurriness and no presence feeling that you're not actually in the VR environment. So the optimization strategy in the industry is reducing MPD via a frequent headgear position updates. And this is they created a term, asynchronous time warp, which is used in every single VR devices on the market today. What it does is really very simple. It's basically instead of generating a new frame, because they cannot do that in terms to match the latency, because a lot of time latency becomes huge. So what it does is actually trick users think that they actually see the correct image frame, but really it was not generating a new frame, but rather project the scene in an updated headgear position. So when you move your head, it will update the scene position, but use the image frame generated from the previous refresh intervals. And we did a lot of research using real devices to see why do we see these kind of motion anomalies happening all the time and make user don't want to stay in a VR, these kind of commercial VR devices. And then we really find something really interesting here. I'll quickly cover this. So typically, when the frame is being processing, the CPU side has an algorithm, prediction algorithm. You will actually understand that at this point, this frame will not fully processed in the next refresh interval. So what it does is it will perform a preemption action, which is at a software level, is a context switch. At a hardware level is a hardware-based context switch. So hopefully you'll finish your context switch on time, and then you perform this asynchronous time warp, which is loaded the previous intervals rendered frame. So in this sense that you will see the frame in the correct position, but to actually reduce the MPD. So your MPD is a little bit longer, but not too bad, right? So this industry design seems to work. But based on our kind of profiling, we find that this kind of preemption process does interrupt the normal rendering process, which is here. And then what it often happens through profiling is that this P, the preemption overhead, is uncontrollable and unpredictable. So a lot of time it pushes the deadline over and over again. So your entire MPD becomes huge. And it's kind of like normally happens in a kind of grouped fashion, where at a certain moment you find the latency becomes unbearable, and then a lot of motion anomalies appear during a short period of time. So real world profiling using the previous figures, we find that this context switch and preemption on average incur about 6 to 18 milliseconds delay across the games, and about 6.44% these ATW operations will miss the refresh deadline. And this is exactly what you see the flashing C in the video, and that's every time you miss the deadline, the C will flash. A lot of people will say, well, it's only 6%, it's not very big deal, but you're realizing that if you are dealing with, let's say, 90 FPS, so you're looking at 100, let's say 120 frames per second, and then you're really looking at a large number of frames every second that miss this kind of deadline. So this is exactly why you see the C being flashing when we're doing the profiling on the real devices. Now, we eventually want to overcome this problem, and we find a way that we can actually use HMC to design this ATW. Instead of launching it on the GPU and interrupting the normal rendering process, we will do it in the HMC. We'll bypass the GPU graphics queues. We'll use DMA directly connecting it with the user's head devices. And on the GPU side, you can let the rendering just perform as long as they want. You don't have to worry about this actual refresh interval. And then on the HMC, because we have a much better way to control the latency, we'll make sure the A will finish before the deadline so that we kind of sort of detach this process from the GPU contention scenario. This is the simplest term to talk about it. And then we actually, excuse me, we actually reduced MTD by an average of 175%. Compared to the current GPU accelerated ATW. In a lot of the cases, we can get very close to 7 milliseconds. Okay, so this is the first work. I don't know how much time I have left. So the next part, really, we did the tethered devices, and then we really want to look at what future, multi-GPU server is going to look like when the era is going to become, we have a large rendering workload, a complex rendering capability is desired at this cloud level. What would be the server design going to look like, and how does it accelerate parallel rendering at that time? So this is the ICT work trying to understand the impact on future parallel rendering system and designs. Sorry, I don't have time to go through details here. Basically, if you look at the paper, we did a lot of trying to understand what the triplet design back then in ICT 19. We're looking at the Grace, what's it called, NVIDIA Hopper architecture statistics, and we're trying to simulate and design this software layer and hardware layer, and how to support a future parallel rendering, and what's the best way of conducting that so that we actually squeeze out the performance without actually encountering large NUMA effects. Okay. All right. The last part is recent work. We did something at the tethered desktop high performance, using Oculus Rift for VR, and we did something for the server side. Around 2020, we have looked at the market again, and then really there's mobile, low power mobile, highly, have a has a higher flexibility to be adapted in the market. And then we're trying to understand how to design this future high quality, low latency mobile VR systems, which you have a mobile VR and you need to actually work together with the cloud services. And on the left side, a Polyrunner runner is one of the typical games that you can purchase on today's mobile devices. And you can see the quality of this is kind of bad, right? A lot of rectangular shapes, and it's not very fancy. On the right side is a high performance GPU rendered VR scene, right? Through a benchmark called Orange Room. And eventually, what we really want to get is you get a VR devices that it's a mobile devices working with the cloud servers. How can we design this so that we can actually have this kind of fantastic high quality scene that's not only presented with high performance GPU rendering. Sorry, need to get through this. And then we did a lot of work to understand the deficiencies of state R. The tethered one, which is the one that first work we're talking about, have very limited movement due to connected cable. We want to focus on mobile VR, and currently mobile VR, both local processing and offloading the workload to remote servers won't work, especially it goes way in terms of end-to-end latencies, that's way higher than the required 20 to 25 milliseconds, and the IPS is also very not ideal. So how do we get there? Some state-of-the-art works has been proposed in recent couple of years. The strategies they're using is they will first design the interactive objects in the VR scene, make it fixed, and then offloading the background part processing onto the remote server. Background is considered a more lighter and a more fixed, and in this way that they will have a decent FPS and decent system end-to-end latency. However, there are two challenges here. In this design, it's not very flexible, and then it's hard to write VR scenes in terms of this design. So basically, you have to reduce a lot of the complexity of what you want to actually design to match the independent hardware that you're running. For instance, people spend 30 to 40% of their development cycles to match this kind of games or VR scenes onto specific hardware vendors' hardware. It's very inflexible. And in this figure, you can see when you design the same object like this tree, there is a real-time user and object interaction factor here. When you get closer to it, the amount of work becomes much more, and it's hard to control. Look at here, we're looking at 12 milliseconds versus 626 milliseconds latency difference. The other challenge is we still find the data transmission from the server to the edge mobile. That's very costly, even for the full resolution background that they actually specifically designed. These are related work. If you're interested, you can take a look from Flashback, which is the older work, to the newer, Firefly and Quarterly. Now we're talking about design mobile system SOC. We're talking about design, how it works with the server side. It becomes an accelerator level parallelism problem. In the paper, we talk about what the static way, which would just, putting the static background in the remote and processing the fixed interactive object, and that's the static state of art, and our QVR. And you can see we tried a lot of things in terms of how to make this to save this purple line of performance, actually reduce the latency in that much. This is just an illustration. So we designed, software hardware co-design to provide low latency, high quality, collaborative virtual reality. And we think about how do we work around in the system on chip that we have. We think about the network latency, and we also considered flexibility and development cycles for VR developers. For instance, people are using Unity and Unreal these days to develop these type of applications. At the software level, we changed the programming model from Unity, and then we provide this collaborative full-weighted rendering framework, and we'll talk about that a little bit. On the hardware level, we redesigned the system on chip a little bit. We put in a lightweight Q-learning based interactive aware workload controller. And then we use the algorithmic similarity driven pipeline reordering and provide a better unified design to reduce the mobile side of latency. Now, I don't have a lot of time here, but what I want to do is to just quickly show you very much. Yep. We really want to show you that the whole full-weighted concept, you probably know that we can actually identify, if we can identify what the human eye is actually looking at and how much this inner circle size would be, which is called the foveal layer, we can actually do this adaptively. So the workload being processed on the edge side will purely depend on the hardware capability at that moment, and also the network latency and the network issues at that specific moment. In this Intel GPU, you can see that for this range of eccentricity, the size of the inner circle, with different workload, you can find a different crossing point for how much inner latency or inner size of the foveal layer could be. And then we change the software framework, rewrite the programming model for it, and then we actually propose a lightweight controller to help us identify how big this inner circle is. We uses the concepts of 6 degree of freedom of our headgear movement. We consider foveal movement, and we then translate them into the simple hardware design. And here is the simple, the details for this. You can look at our paper, and we achieve quite good average end-to-end latency reduction, and average FPS is also significantly improved. And then one nice thing about our design is it can help help the system quickly reach a balance point in terms of local and remote latency balancing point, and then stay that way till the end of every games, right? This actually shows the target FPS, and then through our design, once it reached the stable plateau, the actual frame rate is being really, really nice. Now, here's the sort of the comparison we have. This is just a pure software level implementation because we're working on our hardware prototype for release with DoD. But you can see that if you just do the local rendering, you often see this blur and it cannot really be processed on the local mobile devices. With our strategies, we can definitely do much better, even with just pure software level implementation. Okay, that's all. Visit our website and and then email us if you have more questions. Thank you.
Thank you for so much, Dr. Song. Yeah, that is pretty great job. And also show the solid research result on the future planning scale VR system. Yeah, I cannot wait to search for the papers to read. It's really interesting and meaningful. So any questions from the audience? Yeah, actually, since we have some delay about the schedule, I recommend that if you have any question, you can type in the chat box and interact with Dr. Song here. So I think it's time to us to go on to next talk, and you can type your question in the chat box. Thank you again.
Thank you. And then I probably have to go, but if you have questions, you can send me an email. All right.
Okay, thank you so much. So 1 minute, if you have question, you can ask here. If not, we can move on. Thank you. Okay. Thank you. So it's a way to send the email to Dr. Song if you have any question. Thank you. So yeah, our next speaker will be the first regular presentation. So while I'm making the brief introduction, yeah, can you share your screen, Dr. Roshantha?
Hi. Yes, Professor Yang. One minute.
Hello, Yang, you can share your screen first to give an introduction of
Okay.
speaker.
Yeah, I have that. Okay, I can share the screen here. Can you see my screen? Okay. Yeah, thank you. So our first regular presentation will be by Dr. Hashan Roshantha Mendis, if I pronounce correctly. Thank you. So he is currently the postdoc scholar in the Research Center of the Information Technology Innovation Academia, Sinica, Taiwan. So today he will bring his talk about the Intermittent-Aware neural architecture search. So this work was previously accepted by CODES+ISSS 2021, actually the same conference last year, right? And it has also been published in the ACM transaction on the TECS 2021. So thank you so much, and feel free to share your screen to start your presentation. Thank you. I will stop sharing.
Yeah, give me a minute just to. Can you see my screen?
Yes, we can perfectly.
Okay, thanks, Professor Yang, for the introduction. And in this work, we are introducing the novel problem of intermittent-aware neural architecture search to automatically find deep neural networks that can be intermittently executed on lightweight devices via ambient power. So energy harvesting is a sustainable and low-cost solution for edge IoT devices. However, ambient energy is extremely weak and unstable. So these kind of devices, they experience intermittent power and frequent power failures. And advancements in deep neural networks have pushed inference to the very edge. And even recent research have enabled the intermittent execution of deep neural network inference across power cycles. And deep neural networks have an intractable design space. So the process of DNN design is typically automated using neural architecture search techniques. So therefore, intermittent-aware neural architecture search is a novel and crucial problem to solve to support intelligent and batteryless edge devices. On a typical resource-constrained system, DNN layers are processed as tiles. To compute a tile, the required tile input data is fetched from non-volatile memory to volatile memory, and the computed tile output is written back to non-volatile memory. And to improve inference performance, the tile input data is fetched once and reused across subsequent layers, subsequent tiles in a layer. Intermittent systems execute using the harvested energy in an energy buffer, such as a small capacitor, which essentially defines the energy budget within a power cycle. And when the power fails, the volatile data of the system is lost. So progress preservation is performed during inference, where progress indicators are backed up onto NVM, along with intermediate computation outputs. And when the power is resumed in the next power cycle, progress recovery is performed, where the preserved progress indicators are used to refetch the required input data and resume the interrupted inference process. Typically, a batch of intermediate computation outputs are preserved with the progress indicator to reduce the overhead of progress preservation. So we present a key finding regarding the unsuitability of DNN solutions found by existing NAS frameworks for intermittent systems. We observe that NAS primarily maximizes data reuse to improve inference latency without being aware of intermittent execution behavior. And as NAS does not consider the key costs or the design spaces related to intermittent inference, it may find inefficient solutions which may violate the end-to-end inference latency requirement. And more seriously, maximizing data reuse leads to large and energy-expensive solutions, which may be unsafe because those solutions may exceed the power cycle energy budget and fail to execute. So we present a general principle. To generate and deploy neural networks on intermittent systems, an intermittent-aware neural architecture search should find the right balance between data reuse and the costs related to progress preservation and recovery, while ensuring the power cycle energy budget is not exceeded. Following this general principle, we develop INAS, the first intermittent-aware NAS framework to find DNNs that can be safely and efficiently executed under intermittent power. However, to introduce intermittent execution behavior into NAS raises two key design challenges. The first challenge is how to define a feasible solution space which considers intermittent execution behavior. This is extremely difficult as the design parameters and the energy budget related to intermittent execution are very tightly coupled. And the conventional design parameters, execution design parameters, as well as the hardware and latency constraints need to be considered. The second challenge is how to analytically formulate the performance of an intermittent execution design solution. And this is also non-trivial as the additional key costs related to progress preservation and progress recovery have to be accurately captured. So we address the first design challenge by introducing an intermittent-aware execution design explorer, which introduces a preservation design space and a power cycle energy budget constraint to conventional NAS. The preservation design space includes the batch size of intermediate computation outputs preserved together, and it is unified and jointly explored with the execution design space. The power cycle energy budget is enforced together with the hardware and latency constraints during design space exploration. And we address a second challenge by introducing an intermittent-aware abstract performance model, which formulates the additional costs of progress preservation and progress recovery, as well as computation for a given candidate intermittent execution design. And this allows us to formulate the energy and latency costs of within a power cycle, which in turn are used to derive the end-to-end inference latency across multiple power cycles. So to evaluate the improvement brought by INAS to an existing hardware-aware NAS framework, we deploy the solutions derived by both frameworks on a lightweight Texas Instruments-based real device powered intermittently. Evaluate under 3 different data sets that represent typical TinyML applications. We also conduct experiments under different capacitor sizes and different inference latency requirements to further evaluate the ability of the framework to find feasible solutions under different intermittent execution scenarios. And compared to the hardware and NAS solutions that can safely complete inference, the INAS solutions reduce the end-to-end inference latency by 60% on average. Improvements are more apparent when it is more difficult for hardware NAS to find feasible solutions, such as under a small energy budget and under high latency requirement where conventional NAS typically finds complex networks. By design, INAS does not degrade or improve the accuracy, so the solution accuracy is comparable to hardware NAS solutions. INAS incurs an average of 7% higher search overhead compared to hardware NAS to explore an additional design space and to calculate the end-to-end inference latency across multiple power cycles. So here we present a short demo video that compares the solutions found by INAS and hardware NAS under intermittent power. So in this demo, the intermittent system executes an image classification DNA using only the harvested energy from the lamp. And the runtime information is displayed on the user interface, including the inference progress and status of the power supply. When the energy budget is small, the hardware NAS solutions may become unsafe and are unable to complete the inference, while INAS always ensures the derived solutions can safely make forward progress. When the energy budget is large, the hardware NAS solutions may be inefficient and require a large number of power cycles to complete the inference. In contrast, INAS considers the intermittent execution related costs as well as the preservation design space, so it's able to derive good solutions that always meet the end-to-end latency requirement. And it's also worth mentioning that INAS is an initial attempt at introducing intermittent execution behavior into NAS, and we hope this work will motivate a rich body of potential extensions in the future. For example, model compression techniques such as hardware pruning and quantization-aware training can be integrated easily into INAS to further reduce the inference latency of the solutions. And INAS can also be extended to consider runtime inference adaptation techniques that balance performance and with a minimum amount of accuracy degradation. such as early termination-based techniques based on multi-exit networks. And also to improve search efficiently, recent neural architecture search speed-up schemes, such as differentiable search strategies or search space reduction techniques or concepts such as weight sharing, can also be easily applied to INAS. And it's also worth mentioning that our research group is actively working on enabling batteryless IoT devices to intermittently execute DNNs under ambient power. And most notably, our work on runtime middleware stack referred to as Hawaii enables hardware-accelerated intermittent inference to be accumulatively executed across power cycles. And subsequently, our runtime techniques, which perform model augmentation and inference state information embedding, are able to significantly reduce the overhead of intermittent inference execution. And in this work, our INAS framework automatically finds intermittently executable DNN models. Both Hawaii and INAS have received the Best Paper Awards, respectively, in 2 years in a row at CODES 2020 and 2021. So to conclude, we present the first work to introduce a novel problem of intermittent-aware neural architecture search. And this problem arises due to the unsuitability of existing NAS for intermittent systems that cannot be solved via straightforward extensions to NAS. We provide a general principle to find safe and efficient solutions, which is followed in the development of INAS. We address the design challenge of defining a feasible solution space by introducing an intermittent-aware execution design explorer. And we address the challenge of formulating the performance of an intermittent execution design by introducing an intermittent-aware abstract performance model. We show that the INAS solutions reduce intermittent inference latency by 16 to 87% while achieving comparable accuracy. And improvements are more evident under small energy budgets or when hardware NAS finds more complicated network architectures. And lastly, our INAS framework is made open source, enabling anyone interested to design and deploy DNNs on energy harvesting edge devices. And thank you for listening. And I'm happy to answer any questions you may have. And please contact us for further details. Thank you.
Okay, thank you. Thanks for the super talk. Any questions from the audience? Then Rosh, I have a quick question about the power, the power supply. Then how did you provide the intermittent power supply in the experiment?
Oh, sorry, I closed the screen. But basically, we used a conventional desktop power supply, like a lab power supply to power the energy harvesting board to provide a weak power source to the harvesting board, and then from there onwards, we could generate intermittent. So, like for example, in here you can see. Well, in the demo, we used a direct lamp to power the light. Is using the solar panel is using the light to the light energy to power the device. But in the experiments, we used a power supply, which gives a very weak power source, which is similar to what you get from solar power. To this energy harvesting board, and an energy harvesting board harvests that energy and produces a intermittent power profile.
Okay, thank you. Then did you change the power supply, the power input type in the experiments? I mean,
No. So I guess there's two ways to vary the different profiles of intermittency. So to get like low intermittency or high intermittency, for example.
Yeah.
And in our work, we kept the weak power supply fixed. So that's, for example, at 6 milliwatts. But we did change the capacitor sizes. So one millifarad, 5 millifarads, 10 millifarads, and that essentially generates a high intermittency. So for example, under 1 millifarad, you get a high intermittency. For 10 millifarads, you get low intermittency, which means the system is interrupted less frequently. Yeah.
Okay, thank you. Thank you. Nice, good.
Okay.
Okay, thank you.
Okay. Thank you.
Then
Thanks, sir.
Thank you. I share the screen. Thanks, Rosh, very much. And then we move to the next regular presentation. This presentation is from Xiaoxing Chu. He will give a talk on the topic of keep fresh real-time data retrieval with speed adaptation in mobile cyber physical systems. Then, okay, Xiaoxing, so I think you are already in the Zoom room, right?
Can you hear me?
Yes.
Okay, I will share my screen.
Thank you. So you are from the you're the PhD student from the Southeast University, right? Thank you.
Yes. Thank you. Can you see my screen?
Yes. Perfect.
Hello, everyone. This is Xiaoxing Chu from Southeast University, China. It's my honor to attend the EIC to present our work. Keep fresh real-time data retrieval with speed adaptation in mobile cyber physical systems. In this presentation, I will first give an introduction of the background of the study, including the application theories, the important definitions, challenges, and the related work. In cyber physical systems, retrieval real-time data from physical entities is a common and important mission. Along with the ever-growing scale and the complexity of cyber physical systems, mobile devices such as UAV and UGV become a promising candidate to travel through specific area and collect real-time data of various cyber physical entities on demand, and make real-time decisions based on the retrieved data. With help of mobile devices, we can collect information from the disconnected physical entities, such as bridges, traditional infrastructures in power systems, which are not involved in any network. Additionally, for the sensors like earthquake rescue, where stationary sensors can easily be compromised, or traffic monitoring, where stationary monitoring devices are impossible to be placed. Also, when the sensing task may require multiple types of data, it's economically more efficient to replace many stationary sensing devices with a single mobile device equipped with multiple sensors. It's worth noting that in cyber physical systems, most of the data or the information have timing and performance requirements, such as the real-time deadline for the decision task and the temporal validity of the retrieved data, known as data freshness. Let's look at a simple example. In the early afternoon of a day, the sun is shining and the weather is fine. The data of temperature we collect by some specific sensors are fresh, as the current value can tell the weather right now. However, as time goes by, the sun goes down and the air gets cold. The data we collect earlier in the afternoon is inconsistent with the current century, and it is no longer fresh anymore. Based on data freshness, we define temporal validity interval VI to be the time interval from data OI being retrieved to it be expired. Besides data freshness, data availability is another important property. For data retrieval, a long distance between the transmitter and the receiver sources implies quite a few energy consumption and low successful transmission rate. So typically, researchers use data availability to measure whether a data is available to retrieve. In our work, while mobile device is involved, the data availability depends on whether the mobile device is inside the communication range of a sensor node. We use the location that the mobile device enters and leaves the communication range, SI and EI, to form the availability range, noted as AI. In our work, we consider a speed adjustable mobile device. There is no doubt that the speed adjustment can improve the flexibility of mobile device for data retrieval. However, this also introduces algorithm design challenges during data retrieval and data availability. Let's consider 3 different cases to explain the challenges. For the first case, we assume that the mobile device moves at a very slow and constant speed all the time. This is the availability range for data to be retrieved. The mobile device decides to retrieve the data here and move at a very slow speed till the entire retrieval path ends. This is the temporal validity interval, means that the data is valid for a time of VI from where it is being retrieved. It can be found that the data the retrieved data is already expired because we spend too much time on the path. How about we let the mobile device move faster along the path? Assume that a data item needs 3 seconds to be retrieved. The retrieval time is related to the packet size of the sensor. When the mobile device moves faster and it takes only 2 seconds to pass through the availability range, and the data is failed to be retrieved due to the lack of time. Now, if we allow the mobile device to adjust its speed, the scenario can be more complicated. For example, the temporal validity interval of data 1 is 4 seconds, and its retrieval time is 2 seconds. After taking 2 seconds to retrieve it, the remaining validity of sensor 1 is 5 seconds. Then it takes another 2 seconds to achieve the availability range of data 2, and the remaining validity of data 1 is 3 seconds. If the mobile device spends 3 seconds to pass through the availability range of data 2, the data 1 will remain valid, but the time is not enough to retrieve data 2, as the retrieval time of data 2 is 4 seconds, and 3 seconds is smaller than 4 seconds. Let's reset sometime. If we slow down the mobile device and spend 4 seconds to successfully retrieve data 2, data 1 will run out of its validity and become expired. What if we start the retrieval of data 1 later instead of at the start of the availability range? After taking 2 seconds to retrieve data 1, the remaining validity is 5 seconds. Then it only needs another 1 second to achieve the availability range of data 2. And the remaining validity of data 1 is 4 seconds, which means that the mobile device can spend 4 seconds to retrieve data 2, while data 1 remains valid. From this case, we know that a good algorithm should be designed to properly set the speed and design when to start the retrieval. Here we list some state-of-the-art schemes starting the similar real-time data retrieval problem. All of them have neither 1 or 2 attributes that are not considered in the algorithm design, and we will share the compared results with our proposed schemes later in the experiment session. Next, I will talk about the model and the formal formulation of the target problem. In this work, we study a problem that given a set of physical entities which generate fresh data. A speed adjustable mobile device is used to perform the real-time data retrieval on a given path to retrieve this data while satisfying constraints of data freshness and data availability at the same time. A data item is noted as OI and is associated with 3 attributes CI, VI, and AI. It can be noted that even the moving path is given and fixed. The retrieval order is not fixed, as the availability range may overlap with each other. To formally define the target problem, we give these 4 constraints. First, the real-time constraints. We use F to denote the task finish time, which is the time when all the data item finishes retrieval. The real-time retrieval task has the task deadline D. Apparently, we should have F is not larger than D. Second is the data freshness constraint, meaning that all data items should remain valid till the data finish time. The third one is the data availability constraint. Each data item can only be retrieved within its availability range, SI to EI, where the speed ST is the speed of mobile device. The speed is shown as a curve in this figure, and the area X denotes the physical distance that the mobile device is passing during the data retrieval. Finally, the last constraint shows that the speed of the mobile device cannot exceed its physical limit, S max. We target 2 objectives in this work based on different system requirements. The first one is to find a feasible data retrieval schedule if there exists one. And the second one is to maximize the number of feasible retrieved data items. More specifically, for the first objective, we consider the unit size of retrieval time for all data items and propose a dynamic programming-based optimal scheme. For the second objective, where the retrieval time can be arbitrary values, a fast heuristic is developed. Let's first introduce the main idea of the DP-based optimal scheme. Before we introduce the main idea, let's see the 2 definitions first, block and gap. A block is a time interval that is fully occupied by the data item retrievals. A gap is a time interval when no data item is retrieved. In other words, a gap is the time interval between 2 blocks. The structure of the DP is conducted by blocks and gaps. Given a set of data items with their availability ranges, We first index them in the increasing order of EI. The DP is conducted in a backward fashion from the last block to the first one. These blocks and the gap between them form a subproblem of DP. And plus a new block and a new gap on the left hand of side, we obtain the result of the last subproblem. And this is the structure of the dynamic programming. The recurrent function of the dynamic programming can be derived here. We omit the details, and you are very welcome to refer to the paper for more detailed information. Next, I will briefly introduce the faster heuristic schemes proposed for the general case. We first introduce the major function that is called by the heuristic named function retrieval. This function contracts the retrieval schedule, including the speed and when to retrieve each data item based on a given retrieval. And we prove that this schedule can maximize the number of feasibly retrieved data items. For example, given a retrieval order of 03, 01, and 02 in a backward fashion, the speed can be set to S-max when retrieve 03 because there is no other data item to retrieval. And apparently, the mobile device should also move at S-max during the gap for the chunk of data freshness, and 01 and 02 will be retrieved in E1 to S2 or stop at S2 if necessary to retrieve 01. Then to retrieve 01, then 02 based on the the mobile device will first retrieve 01, then stop to retrieve 02 based on the given order. Now that we know how function retrieval is conducted, the remaining task is to decide a proper order and improve it and call function retrieval. The main idea of the heuristic scheme can be shown as an example. First, we give intentional retrieval order based on EI of the data items. So in this example, the order is 03, 02, and 01. And then we call the function retrieval with the order as input. But found that unfortunately, the 01 is expired in this order. And next, in step 2, we will move the retrieval order of 01 to a later place. In this example, we sweep it with 02 and get a new order. This time, by calling function retrieval, all data items are feasibly retrieved, and this iteration keeps going until all data items are put in a proper retrieval order. Last part, I will introduce the experimental results. The proposed dynamic programming scheme and the fast heuristic are compared with 3 state-of-the-art schemes and the optimal scheme, which is obtained by exhaustive search and a baseline. For the case of unit size retrieval time, we found that DP have the same results as the optimal solution ES, but DP is in polynomial time. For the general case, we found that the fast heuristic named HDRSA performs very close to the optimal solution when the number of data items is in small scale. For the large number of data items, ES cannot output the results in reasonable time, but the proposed HDRSA still outperforms the other schemes in all cases. In summary, this work is the first attempt to jointly consider the data availability, data freshness, and adjustable speed. A DP-based optimal methods for unit size case and heuristic for general case are proposed. In the future, we plan to design approximate schemes to contrast the trajectory of mobile device together with data retrieval to further improve the feasibility and the efficiency of fresh data retrieval. Also, we plan to involve age of information as metric for data freshness to reconsider the real-time data retrieval problem with mobile devices. That's all. Thank you for your attention, and questions and comments are very welcome.
Okay, thank you, Xiaoxing. Thanks for the nice talk. Any questions from the audience? Okay, because the our time is there was a delay from the schedule. Then we move to the next talk. And if you have questions about the topic Xiaoxing presented, you can leave your questions in the chat box. In the Xiaoxing, you can answer them in the chat box. Okay, thank you.
Okay, thank you.
Then let's move to our invited talk 2. Then Dr. Wang Shuo will give an invited talk on the topic of efficient scaling of loosely coupled accelerators for embedded computing. Dr. Wang Shuo is a postdoctoral researcher in the storage research group of Tsinghua University. He received his PhD in the computer science from the Center for Energy Efficient Computing and Application, CECA, in Peking University. His current research interests include compilation techniques for heterogeneous computing platforms and near storage computing. His works have been published at DAC, FPGA, HPCA, and TC. Okay, Dr. Wang Shuo, then please.
Hello, everyone. Thanks for the introduction. Let me share the screen. So, hello, everyone. This is Shuo Wang from Tsinghua University. My talk is about the efficient scaling of loosely coupled accelerators for embedded system. So as we all know, the embedded system is dominated by the tightly coupled SoCs. As we show on the right figure, the SoC contains CPU, NPU, or GPUs. Nowadays, the mainstream processors are based on this kind of architecture. The data transfer and interconnect or data routing based on the on-chip interconnects. This is what we call the tightly coupled SoC. However, there is another approach to couple the accelerators to the embedded system. For example, we can add the accelerators through the PCIe or the other interconnect hubs, such as USB, so on and so forth. As for the loosely coupled SoC, we need to attach the accelerators through the high-speed data transfer link. As we all know, the embedded system are very power or performance constrained. So the options of the high-speed data transfer link is very limited. Only so on and so forth, we only have the PCIe and the USB. And the CPU need to share the main memory with the accelerator as for the programming model. That is what we have currently for the loosely coupled SoC. It is due to the limitation that cause the mainstream SoCs choose the tightly coupled SoC solution. So as for the SoC, how can we scale up the performance for the embedded system? I think from our current research, I think we think that there are two options. The first is we copy the experience from the server side. We attach more accelerators such as GPUs for the server through the PCIe. Since as for the server, we have very high performance PCIe link for the on the CPU side, and then we can attach a lot of high performance accelerators such as GPU to the server system. And another approach that we can directly copy from the HPC system, high performance computing. We can add the accelerator through the networks. For example, Ethernet, InfiniBand, so on and so forth. These two options are not that appropriate for the embedded system, since it requires a lot of devices and also power and a lot of space to contain these kind of devices. So how do we apply the server approach to the embedded system? So we can directly add these accelerators to based on the server approach. We can use the Google TPU, Edge TPU as a case study. As we know, the TPU has two versions, which one is a server version and the other is the Edge version. This is a SoC from NXP, and it integrates SoC and loosely coupled TPU on the right side, and the TPU and the SoC share the DRAM as for the programming model. So the data first transferred to the DRAM and then go to the TPU. So we can abstract this loosely coupled architecture as a right figure. It contains an SoC and DDR as a memory, and we also attach an accelerator to the SoC on the right side. And in this case, we can directly scale up the performance of the SoC via the attaching more accelerators, right? So how do we further scale up the performance? If one edge TPU is not enough for the performance scaling, how can we further scale up the performance? As we all know, for the server solution, we can have a PCIe switch, and based on this switch, we can attach many devices to the switch. As we can see in the right figure, we have add a PCIe switch, and more TPUs can be attached in the system. And based on this solution, we can scale up theoretically or practically the performance of an embedded system. So is this solution appropriate with the embedded system? So let's explore the performance scaling based on this architecture. So we use MobileNet, which is a widely used DNN neural networks for the embedded and mobile systems. And the scaling trend we want to see is that with more TPUs, we can linearly scale the performance, right? However, when we use this solution, the scaling trend as shown by the red line is not very optimal, and it cannot linearly scaling. And what happens during the performance scaling? As we can see, we have the programming model, we have a DRAM, and the data transfer must be go through the DRAM and then go to the TPU. That's one side of the bottleneck, and another is the PCIe switch. As we can see, it is a PCIe 2.0 Gen 2, and the performance is about 500 megabytes. And as for the MobileNet inference task, it requires two kinds of data. The one is the model we use to do the inference, and another is the image. The model, for a period of time, the model is fixed, but the model and the data, both the model and data should be transferred to each TPU. And since the bandwidth of the DRAM is 2 gigabytes. The bottleneck is not here. And the bottleneck is a PCIe link. We cannot have enough bandwidth to support the data transfer of both the model and the image. That's why we cannot linearly scaling the performance of the embedded system. So this kind of scaling strategy. And as we can see, the bottleneck is a PCIe link. Let's compare the GPU and edge TPU because this kind of bottleneck is not very common in the performance scaling of the server side by using multi GPUs. So why does the server scaling approach fail in our embedded system? As we can see, compared with this kind of two architectures, we only need to load the model only once, but the model is very small compared with the GPU memory. So the memory transfer is not the bottleneck for the GPU. And also we have very high DRAM bandwidth in the server side, but we cannot have that much high bandwidth in the embedded system. And also we have very high volume DRAM in the server side. That's why we cannot scale the performance of embedded system. How can we alleviate this problem or solve this problem? We can explore the architecture of the edge TPU. So for the server side TPU, it has a lot of high performance and high capacity memories for the server side TPU V1, V2, V3, and also V4. But for the edge TPU side, we don't have a memory buffer, as we can see on the rightmost side. So since we don't have this memory buffer, we cannot buffer the data. We cannot directly buffer the data from the near edge TPU side, which is the accelerator. So the solution is that we can add a non-volatile memory for this TPU. This is what we. This is our plan. So as we can see, we can add the flash to the near the TPU as a cache or the DRAM. The reason we add this that is the DRAM has a very high dynamic power, and we only need to save the model in the TPU. Since the model we only to load once and use multiple times, and the flash has very low leakage power, and the dynamic power is also 1 or 2 magnitude lower than the DRAM, and the performance of NAND flash is enough for the TPU. So we load the model to the flash, and which is near the TPU. And at this time, we don't need to transfer in the runtime. We don't need to transfer the model from the DRAM to the TPU. We only need to transfer the different image to each TPUs. That's largely alleviated the data transfer bottleneck, and which is the red line is the baseline, and based on our NDP approach, which is a near data processing approach, we can linearly scaling the performance for the mobile net TPU. So that's not the end of the story. This is just a case study. In order to make a one-fit-all solution, we want to explore the different aspects of a design space of the architecture. So we have 3 aspects of design space we can explore. The first is the data transfer bus. It has a different topology to explore for different scenarios. And we have a different local memory type. For the case study we just showed, we use a NAND flash. But for the embedded system, we have a lot more options. For example, SRAM, DRAM, pseudo SRAM, NOR flash, NAND flash, or even the FRAM. And for the local data channel topology, we have different topologies. For example, direct, bypass, or switch. So in the following, I will formulate this problem and make a one-fit-all solution. As for the data transfer bus, we have a different trade-off in the embedded system. If we want to use highest performance and we can sacrifice some power, we can use a PCIe link as a data transfer bus. But for the low power, we have a different solution, such as a USB, eMMC, or UFS. So these can be trade-off for the different solutions. And also we have a design space for the local memory, which is near the accelerator side. In the server solution, the only option we can have right now is DDR or the 3D memory stack solution, which is a HBM solution. But for the embedded system, we cannot sacrifice that much power for the performance. So the only thing we can choose is the low power solution, which is SRAM, DRAM, pseudo SRAM, NOR flash, and NAND flash, and FRAM. The trade-off can be made between the read or write performance, power capacity, and the costs. That's this kind of trade-off is very appropriate for the miscellaneous and the niche market for the embedded system. And also we explore the different solutions for the local data channel topology. For example, we can directly copy the solution from the server side, which is a GPU used, which we call it a direct memory buffer solution. In this solution, the data transferred from the host or DRAM or the host and memory, we must buffer it in the local memory and then transfer the NPU, and vice versa. So in this solution, the local memory must be read and write at the same time, which is more requires the local memory with more bandwidth, but sacrifice the power. But if we sometimes we can use a bypass solution. In this solution, the local memory is not directly attached to the high bandwidth data transfer bus, and we can use another programming cable to directly programming this local memory buffer, such as we program the NAND flash or NOR flash, as we did in the embedded system. In this case, for the mobile net scenario, we can program the mobile net model to each local memory and program once and use multiple times. And the data transfer bus are used for the data transfer, such as images. And we also can use the data transfer bus as a switch. In this mode, the topology is more complicated, but it can support the runtime a local memory update with high bandwidth data transfer. It has a different trade-offs and suitable for different scenarios. So we, as we explore these kind of three aspects, we can make a one-fit-all solution for the embedded system performance scaling. And we use a baseline, which is MLogic developer mode as a baseline. It contains SoC and DRAM, and also an tightly coupled solution, which is on-chip NPU as a performance scaling strategy. And we use our tightly loosely coupled solution, which is we manufactured a NPU scaling board, which is shown in the right side. We use RTSS FPGA as a PCIe switch or USB switch or the other memory link switch, and to scale different NPUs. And the NPUs we use spring spur, and we use NOR flash as a memory buffer. And in this architecture, we can directly scale up the loosely coupled accelerators through this kind of strategy. And this is our performance experiments. We use a roofline model to evaluate our system. And the baseline is shown in the blue line. And we use a different mobile net version, which has different computational intensity, which is how we have used a full kind of mobile net model, which is V1, V2, V3, and V4. And for each mobile net model, our architecture shows superior performance over the tightly coupled solution. And also we can achieve almost a linear performance scaling in this strategy. And that's all. Thank you. And any questions?
Thank Dr. Wang very much. Any questions? Okay, because of progress delay, we moved the QA part to the chat box. So you can raise questions in the Zoom chat box. Thank you.
Okay, thank you. Thanks, Professor Chiu.
Thank you, Dr. Wang. And we send the certificate to Dr. Wang to show our appreciation for the super talk.
Thank you so much.
Thank you. Then we move to the next regular presentation. So let's invite Mr. Kai Liu to give the talk on the topic of an efficient associative memory engine for cosine similarity-based nearest neighbor search. Kai Liu is a senior undergraduate student at the College of Information Science and Electronic Engineering, Zhejiang University. He is currently an intern at University of Notre Dame and the UC Irvine. His research interests include circuit and architecture designs with both CMOS and emerging technologies. Okay, then Mr. Liu.
Yeah, thank you. I will share my screen. Can you see my screen, Dr. Chiu? Can you see my screen?
Yes.
Okay. So hello, everyone.
Yes, yes, perfect.
My name is Kai Liu, and I'm a rising senior undergraduate student from Zhejiang University. I would like to share our research titled An Efficient Associative Memory for Cosine Similarity-Based Nearest Neighbor Search with you. This is a joint work with my advisor from Zhejiang University, University of Notre Dame, and UC Irvine. So as we know, the rate of improvement in microprocessor far exceeds the rate of improvement in DRAM memory speed, which is known as the memory wall problem in the von Neumann machine. On top of that, the data migration arises from nowadays data-intensive world can no longer be neglected. So one possible solution to this is compute in memory. Down, I will show two common design in compute in memory, which are content addressable memory and crossbar. So the first form is content addressable memory, also known as CAM. CAM is a paradigm that merges parallel search into a memory block. Here, I display a ternary CAM design in a context of IP router. So the step one in CAM is to write the data into the CAM. Then the search comes in for parallel search. After the search, the match line, or in this case, the second horizontal line, will have the voltage change and other remains their states. As a result, the output tells the RAM address 01 to that the required output is in address 01, and then the IP router will output port B. This is the first form, and the second form is crossbar. So before going to crossbar, I want to first express how a ferroelectroFET stores 0 and 1. By applying a positive voltage at the gate terminal of ferroelectroFET, we can store a IDVG curve indicated in this blue line. While applying the negative voltage, we can store a IDVG curve in this red line. So when the surge comes in, again, we apply voltage to the gate terminal of ferroelectroFET. For example, if we apply 0.5 voltage to the gate terminal, which is 1. Why? Because if we apply 0.5 voltage, it outputs a high current when the ferroelectroFET stored 1. While the ferroelectroFET stored 0, we output a low current. So this is a AND function. So in this work, we utilize ferroelectroFET crossbar for cosine similarity dot product in the numerator and the L2 normalization in the denominator. Okay, so before it delves into the circuit level design, I would like to sort of express a cross-layer design approach in computing memory. We can look at the stack from bottom up, all the way from devices to applications. For example, we may see what a practical size of a crossbar or CAM is through circuit modeling from SPICE. And we need to ensure that we can map and scale the application to our designed hardware. Also, it is important not to continuously follow the stack bottom up, but also from the top down. Be cognizant of the application needs is also important. So given an application, like the distant function, can the distant function be mapped onto the design hardware? If not, then we need to ensure that the application level accuracy is maintained. Like previously, people in computing in memory, they design hardware kernels for Hamming distance as an alternative for cosine distance. Then people might well need to think of a way to compensate for the accuracy loss. So in this work, we mainly focus on the circuit and application interaction. Okay, so content addressable memory is intrinsically amenable to Hamming distance. And recently, a Euclidean distance-based CAM is presented. On the other hand, cosine similarity is a widely used metric in hyperdimensional computing, feature learning, and text-related application. But cosine necessitates division and normalization, which are not amenable to either crossbar or CAM. So like previous work, they do a lot of the approximation, say in DAC 19, the X-Men paper from Purdue. They kind of approximate the denominator by doing the summation of L1 norm instead of L2, the multiplication of L2 norm. Also in Nature Communication 21, people utilize the application characteristics to approximate the cosine similarity. So these approaches may still lead to accuracy loss. And you may claim that, oh, we can normalize the data first, but in GPU, it still takes milliseconds to do that task. So to express cosine expression in a more circuit-friendly way without affecting the output, we remove the need for square root operation in the denominator without accuracy loss by squaring both the numerator and the denominator. And the input query vector A is shared across the cosine similarity matrix, so we can remove them during the search. So the problem here simplifies into finding a circuit that implements x squared over y. Okay, so now we get into a circuit detail of the work. In this work, we utilize the 1 ferroelectric FET 1 resistor structure that is demonstrated and proposed in Symposium of VLSI 21, which can mitigate variation and makes our design scalable. In order to maintain the correct functioning of the succeeding X squared over Y circuit and guarantee the scalability of the design, we propose to adjust the resistor in each cell. For example, if the array is scaled n times row-wise, then we can maintain each row's current can maintain constant by tuning the resistor in a cell. So by using the F1R cell to form a crossbar, we then use a circuit that can implement X squared over Y, which will be explained in the next slide. But you can see that from the circuit simulation, there's a certain operating region for the circuit. So that's what I'm saying, that we need to adjust the resistor in the cell. And finally, we use the winner-take-all circuit for nearest neighbor sensing. And from the circuit level simulation, we can see that approximately 10% of the error is introduced by the design hardware. So this slide, I sort of go into more detail of the analog circuit. So the left shows the analog translinear circuit that implements X squared over Y. So this circuit mainly consists of a translinear loop, which is indicated by the blue arrow here, including a clockwise transistors M1 and M4 and counterclockwise transistor M2 and M5. So the transistors along the loops are operating in subthreshold region, which can be characterized by the expression in equation 1. And by rewriting equation 1 to equation 2, and we substituting it into equation 3, which is a Kirchhoff current law, we can finally get the X squared over Y expression. So that's for X squared over Y circuit. And the right shows the current mode winner-take-all circuit without feedback. So if we assume the first input rail has the largest input current, then the gate voltage will be here in V sub C will be driven to a higher level. And other sourcing transistors drain terminal will be driven to a lower level in order to maintain the smaller current relationship. As a result, the reduced drain voltage will drive less output current through T sub 22 and T sub 2M in this case, while the T sub 21 will have the largest current output. So by employing a current mirror as a feedback, we kind of as the output current into the input again, thus further exacerbating the current difference in the input rail. So here we show the overall design of our cosine. So the upper left array is for cosine numerator, namely the dot product, and the left is for the cosine denominator, the L2 normalization. Since the L2 normalization of the binary vector is simply counting ones, so in this case, during the search, the input of the Y array or the right array is simply all ones vector. Then the output current then feeds into the circuit we just discussed above, the X squared over Y circuit, and we feeds into the nearest neighbor sensing search circuit. So here we summarize the search energy per bit and search latency of different associative memories with different similarity or distance metrics. The results shows that our cosine design offers 90.5 times energy saving and 333 times less latency compared with the approximated cosine similarity search engine proposed in Nature Communication 21. And in comparison with the existing associative memory that implements Hamming distance, or recently proposed can implement Euclidean distance, our design is also superior in terms of energy and latency. The significant improvements of our design mainly benefit from following aspects. The first is like the advantages of ferroelectric FET in write energy. And the second is one ferroelectric FET, one resistor structure, limiting the conducting current in the memory, thus, improves the energy efficiency and the functionality. And the final one is that we have a simple analog circuit design compared with previous other design, which includes capacitor and analog to digital converter. So that's three merits of our designs. So to validate the effectiveness of our cosine design as an associated memory at application level, we further benchmark our design in a context of hyperdimensional computing, or HDC. HDC is a general model of computation with high parallelism and is robust to hardware noise. And it can be used in a variety of scenarios, including classification, clustering, regression, reinforcement learnings, and recommendation systems. For HDC classification, the first step is to encode the data into high dimensional space. Then HDC performs a learning task through a single path training. The training generates a hypervectors representing each class. Then during inference phase, the search data comes in, which represents the data that need to be classified, is searched across the stored hypervector to find the highest similarity in terms of cosine. So we evaluate the HDC classification and efficiency over 3 large-scale data sets, HAR, phase, and isolate. The results are reported using our proposed cosine similarity, or the common design in hardware, the Hamming distance, as the similarity metrics. Our evaluation shows that by using cosine similarity, HDC achieves significantly higher accuracy, or on average here is 7% compared to the Hamming distance metric. And down figure B and C shows the energy efficiency improvement and the speed of comparing to the running on the NVIDIA 1080 GPU. So our result indicates that the associated memory using cosine provides higher speed up and energy efficiency in the higher dimensionality, which is 1024. For example, cosine achieves 47.1 times higher speed up and 98.5 times energy saving comparing with the NVIDIA 1080 GPU. Regarding the circuit level variation, I just talked about the 10% error. Notice that in such application, the HDC application, it is robust to noise. So where we evaluate and it is, have no impacts on the final results. So in conclusion, I think there are several distant metrics that is used that are used by different applications in software right now, but hardware people like in the field normally just bypass these cosine similarity simply because of its complexity in hardware design. So I think this is a simple work, but just giving a general cosine associative memory design that has not been presented before, which is really exciting. And the evaluation benchmarking results at array and application level show the robustness and superior accuracy to Hamming distance implementation. Also, like I said, this is a relatively general design. This is not limited to a certain application, not limited to a certain NVMs. This is rather general. So the final thing is that breaking down the work length of the array is left for future work, as it's still a really important issue to be coped with. So yeah, that's all for today. Thank you for your attention.
Thank Mr. Liu for the exciting talk.
So any questions?
Yeah, well, because of a delay, still we moved the question part to the Zoom chat box.
Sure.
Okay.
Thank you.
Yeah, thank you. Then let's move to the last presentation. Let's invite Mr. Huichuan Zheng to give a talk on the topic of lifetime improvement through adaptive reconfiguration for non-volatile FPGAs. Mr. Huichuan Zheng is currently pursuing the PhD degree with the School of Computer Science and Technology in Shandong University. His research interests include non-volatile FPGA and FPGA logic synthesis. Okay, Mr. Zheng, let's start. Thank you.
Can you see my slide?
Yes, yes, perfect.
Okay. Hello, everyone. I am glad to have this opportunity to deliver this talk. I am Zheng Huichuan from Shandong University. The title of my presentation is Lifetime Improvement through Adaptive Reconfiguration for Non-Volatile FPGAs. Due to the advantages of great flexibility and low power consumption, FPGA has become popular in many fields, such as the 5th generation wireless, cloud computing, embedded vision, and others. These complicated applications need a great number of resources, especially the on-chip memory. So the requirement on the memory capacity is continuously increasing. Take the Xilinx commercial FPGA chip as an example. The capacity of block RAM has increased from 10 megabits to 400 megabits. Besides, with the development of process technology, the leakage power becomes a critical issue, which may even exceed the dynamic power. To address these problems, researchers propose to replace the SRAM in FPGA with non-volatile memories. Compared to SRAM, non-volatile memory has advantages of high density, low static power consumption, and non-volatility, which brings the opportunity to break through the bottleneck of the on-chip memory. The access time and endurance of non-volatile memory is inferior of SRAM due to the increasing complexity of peripheral circuits and increasing memory capacity. The operation frequency of SRAM declines rapidly. So in large memory, the access time of non-volatile memory is near to the of SRAMs. For the endurance, without any optimization, non-volatile memory will be broken much earlier than SRAM, where leveling has been well studied, which aims to enhance lifetime of non-volatile memory through balancing writes across different physical regions. So the lifetime is not limited to those few early warned portions. In this work, we will focus on the lifetime enhancement for non-volatile memory based on block RAM, based block RAM. For FPGA, where leveling mapping, we can it can be achieved by multiple reconfigurations. Different configuration file has different physical to logical mapping. By switch though among these configuration files, we can change the mapping relationship. Typical well leveling methods are achieved by remap the logic code data to the physical code block RAMs. This mapping is according to the predicted workload that relies on the static analysis. For the static analysis-based well leveling, it generates multiple configuration files at the offline stage. At this stage, static analysis is applied to predict the runtime write distribution. They generate some random excitations to the circuit's primary inputs. By this way, the write frequency of each block RAM can be calculated. Then they investigate the well leveling strategy in the placement stage. The strategy generates multiple configuration files according to the predicted workload of block RAM and switch among them according to the predicted order. However, the static analysis will not be accurate enough for the applications with multiple runtime working patterns. This is a motivation example. The application will have different working patterns in different application environments. This figure shows the normalized block RAM write frequency of one circuit benchmark under 20 groups of random excitations. Due to the lack of runtime information, such as input, static analysis-based well leveling method cannot fully explore the benefits of logic to physical DRAM mapping. So in this work, we are committed to the scenarios that write behavior relies on the environment. At the offline stage, we will rely on the sensitive tools to generate a set of configuration files. At runtime, we adaptively select configuration files for reconfiguration so that writes can be balanced among block RAMs. The key idea is to match runtime patterns with features of configuration files. To achieve that, we modified the placement algorithm in the sensitive tool to generate configuration files with various features, such as different logic to physical mapping. Then we developed a decision maker which perceives the runtime pattern and select the best configuration files, so that in a future period, hot logic block RAM can be mapped with cold physical block RAMs. First, we should generate multiple configuration files at offline stage to match the runtime patterns. We wish to get different configurations for adaptive selection. From the lifetime's perspective, the difference means configurations use various physical DRAMs. In this case, writes can be distributed to different areas when running these configurations. Placement is a key step to determine the physical to logical mapping relationships in the synthesis tool. So we propose to introduce this idea into the placement algorithm to generate configurations with various features. The traditional placement in CAD flow is simulated annealing based, which with logical blocks stacked. As the first step, the initial placement is generated. This is random. Then two blocks are randomly selected and swapped. The design will be accepted if any benefit can be gained by this swap. This swap and evaluate procedure are iterated until the benefit is little or the iteration number is met. The benefit of swapping is evaluated by a cost function. We will inject the lifetime consideration into the cost assessment. The use cost represents the cost of the used number of echo logic block RAM. The more times block RAM I is used, the greater cost of choosing it will be consumed. This guides the logical block RAM to be mapped to those physical blocks that are less used. In addition, to generate more different placement solution and increase the decision-making efficiency, the reuse cost is introduced. This will prevent logical blocks from being mapped into the same physical block RAMs in multiple configuration files. We will save the information that's needed for the cost calculation. At runtime, we randomly select a configuration file after a period of time. We make an observation. The observation means to get the current write pattern by counting the number of write-enable signals. We use the decision maker to match the configuration files to the working pattern. Decision maker will select a sequence of configuration files from the candidate queue to reconfigure. The block RAMs where leveling can be modeled as this formula, where the matrix curve represents the historical write workload of the physical block RAM, and the matrix count represents the normalized write load of the physical block RAM after reconfiguration. And the matrix W is the weight of the execution time of each configuration file. The product result represents the future write load after reconfiguration. We hope that after multiple reconfiguration according to this weight, the block RAM's normalized write load can reach 100%. Up to some mathematical transformation, we can transform the problem into this formula. This is a typical quadratic programming problem, and there are many efficient FPGA solutions. After that, we record the weight of the configuration and give priority to those files with high weights. When the counter reaches the threshold, we make a new observation and make new decisions. In particular, the more time of observations and decisions are made, the more accurately the work patterns can be perceived. But observation and decision making can also bring additional overhead, which is also a trade-off. In the experiment, we set the threshold to 10%, which will hardly affect the operation of the system. In the experimental section, we integrate the post-pattern-aware leveling into the open source BTR7 CAD flow, and we set the performance-aware leveling strategy as a baseline. And this is a lifetime enhancement of each test bench. The data are normalized to those of baseline. On average, the proposed method can achieve 120% of lifetime enhancement, which benefits from the collaboration between decision-making and the lifetime-aware placement algorithm. Our method can generate a large number of configuration files. Generally, higher lifetime improvements can be achieved with more configuration files. However, it needs more memory space for the file storage. So we set a group of experiments to explore the performance with different number of the configuration files. the strategy our light to it will generate fewer configuration files than the baseline, and our heavy can generate more configuration files than baseline. The proposed mechanism has more performance overhead than baseline, and the performance overhead increases as the increasing number of configuration files. In practice, we can decide the number of configuration files to the available storage to achieve a trade-off among lifetime improvement, performance, and storage overhead. With the increasing number of configuration files, our method has more lifetime enhancement. In particular, the decision maker brings a more significant lifetime enhancement, since more configuration files increase the solution space at runtime. And that's all my presentation. Thanks for your attention. If you still have any questions,